Yeah, great. Okay, so Gokul is a fifth-year PhD student at CMU. He works with Stephen Wu and Drew Bagnell, who is also my PhD advisor. He's going to tell us something that he's very excited about, which is the value of RL in fine-tuning language models. With that, Coco, please take it away.
Yeah, thanks, Wen. This is going to be a somewhat unusual talk for me because this was also a somewhat unusual paper for me. When we first started thinking about this question, I think we thought it was going to be, sort of a victory lap paper, pretty easy to write. But the more we thought about it, the deeper and more complicated it got. Um, so a lot of this talk is really going to be me trying to walk you through the process it took us to get to the final answer that we think is the most compelling. Because I think I could just tell you up front, but I don't think it'd be as convincing then. Um, I do know one thing about this presentation, which is that it has a lot of slides in it. So I'm going to ask if we can keep all questions till the end, if that sounds good. All right. So, um, I probably don't need to belabor this point, but I think it's accurate to say that we live in the era of fine tuning. If you spend nearly as much time on Twitter as I do, you'll see lots of memes like this where, you think of your base model as being some sort of like, um, blob of text. Somehow you can make it put on this happy mask and actually start doing the right thing with fine tuning. As of I guess yesterday, this meme is now out of date. We're up to GPT 4.5. But you still see the same sort of paradigm there, right? Numbers might change, but the overall operation is the same. We have some base model, and then we get some data that tells us, okay, we want you to do this particular set of things. Um, Now, there's a lot of examples of the value of fine tuning and what it can do, but I thought I'd just shout out a few from my own work and from folks I know. The first is from some work here at Cornell. So you might think of something like a Bayes consistency model being able to give you generations that look like this. They're reasonable. They kind of like look like the animals you'd expect. But with some sort of fine tuning process, you're able to instead get these sort of much more, let's say, aesthetically pleasing images. Um, this kind of holds beyond just image generation, also holds true in robotics. So this is an example of some of my own work, where on the left we have some sort of base model, and on the right we have some sort of fine-tuned model. And you're able to use fine-tuning to get sort of very complicated behaviors out of these sort of systems. So on the left, it grasps the cup by the handle, but it grasps it in a really imprecise way that kind of lets it slide down later. But with fine-tuning, I'm able to say, okay, grasp it in a stable way. Um, and you can also, and perhaps this is the most well-known example of this sort of stuff, right, is do this for language models. So you might start off with, some sort of prompt sort of thing that says, okay, what is the purpose of this code, right? And you're going to get these sort of like very sort of not useful descriptions of what's going on. But with some human feedback, you're able to eventually get this sort of thing that like actually, is closer to what we actually want the machine to do. And again, you see the sort of paradigm of some base model trained on a lot of data from the internet being okay, and then you fine tune it to do something you actually want. Um, so I think if you look at the plots in the papers sort of underlie the systems we kind of use today, you'll notice something interesting. So you'll have some sort of base model. Maybe you do some sort of offline fine tuning on a little bit of data, but there almost always is this step where you use reinforcement learning, and this is what leads to the most important and sort of critical performance gains. So I'm going to maybe modify my original statement and say that we live in the era of reinforcement learning based fine tuning. So just so we're all on the same page about the pipeline here, we're going to, for example, maybe first do some sort of supervised fine-tuning procedure where we just collect demonstrations of the right way to complete a prompt. We get some text, we pay some smart people to tell us what we actually wanted you to say, and then we use this to just sort of like fine-tune our policy a bit, just via standard next token prediction losses. Um, then once you have something that is kind of reasonable, what you usually do is you say, okay, I'm going to give you a prompt. I'm going to sample multiple completions from the policy. I'm going to ask some sort of labeler or rater to say, which ones did you prefer compared to the other ones? So this is just a kind of a classification label you can think of. And then you use this data to train a reward model or a classifier. Then what you do is you then use this whole kind of learned classifier, this learned word model, to provide on-policy labels for some sort of downstream fine-tuning procedure, which is done via reinforcement learning. So you get a sample from your policy of how to complete some sort of prompt, and then you say, okay, according to my word model, this is how good it was. I can now compute a policy gradient, do updates, things like this. Um, and I want to maybe kind of pause here and note the sort of universality of this paradigm, right? It's not just GPT-3 and higher values of 3. It also works for like, the Gemini models, the DeepSeek models. Everyone is doing this thing, right? Um, so the question I really want to kind of get into today is the following. Um, what is the value of reinforcement learning for fine-tuning? I think when I first started thinking about this question, I thought the answer was really obvious. Now I am much less convinced it's obvious. And part of the goal of this talk is to convince you that there is an answer, there is a good answer, but it's not the one you might initially think. Um, so fine tuning is a very broad kind of paradigm. There's a lot of different things. We use it for things from reasoning to just, I guess, code completion at this point. I want to focus on a specific kind of fine tuning called preference fine tuning now. Um, all the arguments I'm going to make in this section, and for the rest of the talk, apply much more generally, but I think it's easiest to ground them in maybe an application or a way of doing fine tuning that people are more familiar with. So we're going to have some sort of question in, I guess NLP terms, we're going to call this a prompt. In reinforcement learning terms, we'd call this initial state, sampled from some initial state distribution. Um, and then what we're going to do is we're going to generate autoaggressively. So we're going to pick some token, let's say A1 in what we call our action space. Uh, and we're going to keep doing this over and over again. Um, and we're going to do this for some number of steps. And then we're going to call this a completion to the prompt. So really, you can think of this as sampling a trajectory from a policy condition on some initial state if you're a reinforcement learning person, or sort of autoaggressive generation of on top of a prompt if you're an LP person. And you can do this multiple times. Now you have two. And then you can ask a person, okay, which of these did you like better than the other? And you can tell by the sort of little wheel in their head, they're thinking really hard about this. And they might tell you, okay, psi 1's referred to psi 2. Psi here is how we pronounce trajectory. This tells us that this label here, that this sort of top trajectory here is referred to this bottom one here. So kind of put together, we're going to have a data set that looks something like this. We have uh, completions to the same prompt, and we have labels of what completions would refer to other completions, where these labels are often generated by asking a person. There's nothing special in this talk about the fact that you're getting human feedback here, other than the fact that for a lot of things we care about in practice, it's very, very hard to sort of have an automated evaluator. Maybe for something like certain sort of coding tasks or reasoning tasks, that's okay. But for the sort of like, generate an aesthetically pleasing image style of tasks, it's very hard to do that other than just asking people for feedback on what they find pleasing. So that's maybe the overall setup of what I'd call preference fine-tuning. This is how we get the data set. And now I'm going to talk about how we actually do optimization. Yeah, but before I do that, does anyone have any questions about the high level picture of what we're doing here? Or else a lot of things are not going to make sense. Okay, cool. So, uh, given the prefix of this talk, you might think that, you know, fine-tuning can kind of promise you anything and everything, and depending on the amount of, VCs that you listen to, it can. But I am going to try and, be a real academic about this and sort of simplify it down to what we're actually doing. All we're doing in preference fine-tuning is maximizing the relative likelihood of preferred completions to dispreferred completions. That is all we can do, right? That is the only kind of data we saw. That is all we could learn. That's it. So when you think about it from this perspective, and I'm going to abuse notation throughout this talk, apologies in advance to anyone who is, a more proper theorist than myself. You can think of this as basically saying, okay, I want to pick some policy, pi, that basically, maximizes the likelihood or minimizes the KL divergence to my sort of offline collected data set D. So really what we're trying to do here is maximize the data likelihood or minimize the KL divergence of the data. Now, if we had data everywhere. Like I got you to compare every possible completion to a prompt, and I, paid people a truly insane amount of money to do this. This would be all we need, right? Because then I would have labels on every possible thing we could care about. However, in practice, getting a person to tell you what every single sequence of tokens compared to every single other sequence of tokens, how good those two are, is really, really hard. So we usually only get a data set with less coverage than all trajectories. And then we often add in this sort of regularizer here, where we say, okay, I want you to try and stay close to maybe some policy that's good, some policy that generated the data often, some sort of prior regularization. The exact, sort of identity of what this prior is doesn't really matter for what I'm going to talk about today, but just think of it as a policy you don't want to stray too far from. Um, and I think that like if you have maybe more of a theory background, you can view this in a bunch of different ways. This is really just online mirror descent or follow the regularized leader. You can also think of it as a variational approximation of just Bayesian inference. But don't worry too much about that if none of those words made sense. Really just think of this as just a kind of regularized maximum likelihood estimation. Um, and because I want to keep this talk not too math heavy, I'm going to also ignore the prior regularization for the majority of this talk. It doesn't end up mattering as much as one might think. So given this data set and given this overall objective of what I want to do, right? I think the most logical thing would be to say, okay, can't I just do maximum likelihood estimation here? Can't I just, maximize the probability of preferred completions and dispreferred completions over policies? And this is often called offline preference fine-tuning. There's a bunch of different versions of this. Perhaps the most iconic and the most well-known is DPO, direct preference optimization. Um, there was a period, maybe like 2013, 2014, where everyone and their advisor had their own sort of like version of star PO. There was like IPO here. It got bad enough that we exhausted the entire English alphabet and we had to start switching into Greek letters. Um, uh, if you know who the authors of that paper are, you know why that is funny. But I don't want to maybe talk too much about the details of any particular kind of fine-tuning algorithm today. Um, I think all the people who wrote all these papers are much better theorists than myself, and they could tell you why you should prefer a square loss to a hinge loss to a chi-squared loss. I'm going to try and kind of simplify things down here so we can really get at what I think is the heart of the issues with offline fine-tuning. And to do that, I'm going to ignore a bunch of details and say, roughly speaking, offline preference fine-tuning is really just maximum likelihood estimation. So um, I'm going to draw some sort of pictures here that kind of capture the vibe of what I'm trying to say. Again, nothing too formal. So I'm going to say our data set D is maybe some point in space, and we can think of having some kind of space of policy. And really what we can think of maximum likelihood estimation as doing is projecting onto the space of policies under this sort of forward KL metric. So we're going to say, okay, try to find the policy in my policy class that maximizes the likelihood of the data. Um, you can also do this for fitting a reward model. So again, what you can try to do is say, okay, I'm going to try and maximize the likelihood of my data over reward models in my reward model class. And you're going to get some maximum likelihood estimates there. Uh, now, I think the first kind of response you might have if you haven't seen this stuff before, or even if you have, is that this seems like kind of like there's a type mismatch here, right? I'm using a bunch of different symbols that all are of different classes. So let me make it a little bit more formal now. So policies here are going to be maps from states, aka prefixes, to distributions over next tokens. And then live in this policy class, big pi. Rewards here are going to be maps from like the full completion in the prompt. That's what this like larger uppercase psi means. The set of those really to scalar values. And they're going to live in this class mathcalar. Um, and I'm going to come back to this point later, but just keep it in the back of your head that both of these are often fine-tuned for the same SFT checkpoint. So the backbone of both of these things is in practice almost always the same thing. So in a slightly more detail, there is this model of preferences called the Bradley-Terry model, which says that the probability of preferring one completion to a prompt over the other is equal to the sigmoid of the difference in rewards. For a variety of reasons, I do not think this is a reasonable assumption to make, but I am going to sort of ignore those issues for most of this talk. You can ask me afterwards if you have questions about what I think is better. Um, so given this sort of likelihood function, it's pretty reasonable for me to write down a loss for reward models, right? I can just say, okay, I'm just going to minimize the cross entropy between the data set and my reward model. Simple, right? This is just standard supervised learning. This is really just logistic regression, fitting a classifier, something hopefully everyone's done before. It's a little bit more tricky when you do this over policies. What people end up doing is basically they say, okay, the probability of a completion under my policy is just the product of the tokens probabilities, right? There's no dynamics here. I don't need to factor that in. I can then say, okay, I'm going to define something. I'm going to call it r pi, which is going to be the log of that probability. I can take the log of a product and break it up into the sum of the logs. That gives me this guy over here. And then I can also define a kind of an equivalent loss function over these sort of like kind of pseudo reward models. I'm going to call them local reward models and compared to global reward models that look at the whole trajectory at once. Um, that basically say, and I can use that sort of, token-wise reward model and feed that into the same sort of like classification, logistic regression style loss. So the details of this don't matter too much if you haven't seen it before. At the high level, though, I think the point I want to get across is that for fitting both policies and reward models, this is really just logistic regression / classification. So nothing fancy, nothing unusual, just that. Um, so uh, I think that if you think about it from that perspective, we kind of have parts of the picture that, we're really projecting a data set onto the space of policies and onto the space of reward models via this sort of forward KL metric, just maximizing likelihood. I'm not going to state something without proof. The proof is fairly simple, but I don't want to go through it live. And it's that soft reinforcement learning, aka entry regularized RL, is really a reverse KL projection. So the sort of step where in RLHF, where we go from the learn reward model to a policy, really can just be seen as a projection under the sort of opposite order of KL. That gives you this policy, pi hat RLHF. So I think the right way to think about RLHF is really that end to end. It is first doing a forward KL projection onto the space of reward models, and then doing a reverse KL projection from that learned reward model onto the space of policies. Um, the I think natural question, given this picture, would be okay. At the end of the day, I want a policy, right? That's what I'm trying to get. That's what I need to give. Um, why would I ever go through this detour through reward models, right? Um, I think the answer to this question is very, very subtle, and it's really what I'm going to spend the rest of the talk talking about. But I just want to sort of maybe raise that question first in your head. Now, that's a really complicated question, it turns out. I want to start with a simpler question, and that's going to be just when is the maximum likelihood estimate directly over the class of policies going to be the same as the sort of output of this two-stage procedure? So again, I'm going to state this without proof. There's more formal versions of this sort of in the actual paper. But if the set of policies and the set of reward functions are sort of one-to-one mappings, they're sort of isomorphic, by which I mean you can think of the trajectory level rewards you get from using a sort of global reward model and the sort of reward functions you kind of can back out from a policy by summing up its next token logits over the whole generation. If those two things cover the full set of cover the same set of functions and all projections are exact, then these two things should give you the same output. If you've taken a statistics class before, you might have heard this stated more formally as maximum likelihood estimation is invariant to reparameterization. Um, so just to give you some intuition for why this should be true, um, if, pi and r are basically the same class, and I tell you that the secondary reverse KL RL-based projection, the blue arrow, is lossless, right? It basically means the first step gets you to the same point as pi hat Emily, and the second step doesn't lose you anything, right? So both of these should essentially do the same thing end to end. Um, so that is the I really overuse the word vibe, but that's the vibe I'm trying to go for here. You can state this all much more formally, if you like. So um, this seems interesting, and you might say, okay, this is cool, a bunch of information, geometry, some pretty pictures. That's nice. Well, why should I care about this fact, right? And I want to now connect back to what I was saying earlier, which was that in practice, policies and reward models are just fine-tuned from the same SFT checkpoint. Like all you do to get a reward model is you take the policy you got out of SFT, you remove the final softmax, and you just like stick a linear layer or a shallow MLP on top of it, and you have a reward model. So up to like one linear transformation or like minus a softmax, these two are actually the same function class. I'm using the same data to fit these things. I'm using the same function class to fit these things, roughly speaking. Um, and yeah, I'm using loss functions that look really, really similar to fit them as well, right? They both just basically look like logistic regression. So I think the reason this is sort of the stuff I was saying in the last slide is interesting is that like it's much closer to the reality of what's happening in practice than it might initially seem. So uh, I also want to note that like this sort of all projections exact thing is a really strong assumption, right? It's assuming I can do reinforcement learning perfectly, globally. Um, and I would argue that really this detour can only cost us, right? Like the only thing that can happen is in practice is that I'm going to not do the RL step exactly perfectly, right? So um, it seems like, taking this detour through a word model, when I have these sort of equivalent classes, doesn't really give me anything and can only really hurt me because I have to also do the secondary RL step. Um, if you have sort of a background in information theory, you can really think of what I'm saying here as just a variant of the data processing inequality, which basically says that, passing through an extra kind of chain, part of a chain, basically can't give you any new information, right? Um, So maybe to just summarize the sort of the point I'm trying to get across here, I would say that, when do all roads lead to likelihood in the title of this paper, it's when policies and rewards are isomorphic. When these two basically cover the same function class and we expect every kind of optimization thing to work perfectly. Um, so this is, where we were a few months ago. Um, and we spent a long time being like, because we seem to see these two things that are happening that are contradictory, right? We have all the incredible kind of fine-tuning things, both examples I showed, and just more generally, all these sort of models that use reinforcement learning for things. Um, and given how much of a computational burden and hyperparameter tuning is required to do RL, it'd be really, really weird if people were doing that just because they felt like it. There wasn't like some more like fundamental underlying reasoning why this was actually useful. But we have to square that with when we look at it from an information theoretic perspective, there doesn't appear to actually be any benefit from doing this, right? All we've said is that we've introduced an extra step into what could be a one-step process, and that can only introduce extra errors. So, um, you know, uh, this was the part of this project where I decided to do something I hadn't really done before, which was that I decided to do science. Um, so I'm gonna date myself a bit here, but I think of, Mrs. Frizzle as being the patron saint of science. And yeah, we spent a few months sort of taking chances, making many mistakes, and getting very messy. Um, so, jokes aside, what I'm going to try to do now is do a set of kind of more controlled experiments about what is really leading to this gap between online and offline performance in practice. Um, so a little more concretely, I'm going to focus on the task of learning to summarize from human feedback. We're going to basically look at summarizing some sort of Reddit posts, and we're going to fine-tune models from the Pythia family, train on this, or pre-train on this large data set called the pile, which has, a bunch of nonsense in it. Um, And to get as close as we can to this sort of isomorphic classes setting, um, I'm going to try and kind of eliminate as many possible confounders as we could have that I think have shown up in either prior results or maybe part of the overall story that I think don't get at the heart of the actual question. So I'm going to use the same data set to train both the policies and the word models. I'm going to start from the same SFT checkpoint to train both. And perhaps most critically, I'm going to use the exact same optimizer for both online and offline fine-tuning here. So I'm going to use DPO for all the experiments in this paper because of sort of the practical ubiquity of this algorithm. So the sort of offline DPO thing I just described, you can think of as just being a regularized version of maximum likelihood estimation. Um, the online version of DPO that I'm using for policy optimization here is a bit different. So what I mean by online DPO is the following procedure. I am going to take my policy. I'm going to sample a bunch from it. I'm going to rank those samples via my learned reward model. And then what I'm going to do is basically say, okay, what was the highest ranked sample and the lowest ranked sample? I'm going to take those two, use that to construct a new preference data set, and kind of pass that back into the same sort of maximize the likelihood procedure. Um, the reason I'm doing this particular way of optimization here is that a lot of the studies you'll see comparing online and offline preference fine-tuning kind of introduce the confounder of using a different optimizer, let's say PPO, for the on-policy stuff. And I think it's like a very, very hard to actually have an apples to apples comparison when you're using a completely different optimization algorithm for the online and the offline things. So I'm trying to eliminate as many possible kind of extraneous factors, I think. That is to say, I'm not in this paper trying to actually shoot for getting like the best performance on any particular benchmark or something like this. I'm just trying to understand what is it fundamentally that led to a difference between online and offline algorithms. Um, so um, turns out that, despite the fact that we can't really say what OpenAI is doing beyond what we see from the tech reports, even in experiments we can independently reproduce ourselves, the gap appears in these sort of apples to apples comparisons. So I'm gonna put up some numbers on this slide, and I'm gonna try and explain what they mean. So the metric I'm gonna use here is a win rate against human reference summaries on kind of unseen prompts as calculated by GPT-4o. Um, and what you'll see here is that when you go from supervised fine tuning to DPO, you get some improvement in performance. If you do two iterations of DPO, this DPO 2x thing, you do a little bit better. So, two epochs over the same data set. But when I switch to the online versions of DPO I just described, where I sample from a policy, I rank the completions, and I use that to do more and further optimization, I see an improvement in performance. Um, and it turns out you can do this with the base policy for this online DPO step, either being the SFT policy or the DPO policy itself, and you still get improvement. Um, and this, I think, is really interesting, right? Like, I'm training the policy and the reward model on the same thing, but there's more to squeeze out of the reward model in the sense that I can further optimize the policy based on the reward model, even though everything had the same backbone, was trained on the same data, things like this. Um, and the reason we had this sort of DPO 2x comparison here is that, you might just argue that we're just doing more steps of gradient descent here, right? But no, everything here, the last 3 bars in the first plot are taking the exact same number of steps of gradient descent. I'm also using the exact same hyperparameters and all the other stuff you'd expect across all of these experiments. The same thing holds true if you make the models larger. Um, Another kind of maybe question you might have is like, okay, um, well, maybe there's something sort of unique to online preference fine-tuning that makes it easier for it to do well on this GPT-4o win rate thing, right? We could be hacking the evaluator in some sense. To sort of guard against that, I actually calculated the sort of fine-tuning objective I talked about in the previous slide. You can just sample a bunch from your policy to estimate the reverse scale divergence. And even then, you will still see that like when you take GPT-4o out of the evaluation loop, there is this robust gap in performance between online and offline reference fine-tuning without any other sort of extra data being introduced into the system. So I would say the takeaway from this is that like even beyond the sort of things you see kind of like the large scale systems, even in the sort of like smaller kind of things we can do in academia, you still robustly see this gap. So, okay, so we've seen this gap here. We have the theory we talked about before. We want to now explain what is this gap between what we saw in theory and what we're seeing here in practice. Um,
Can I
and
ask a can I ask a quick question?
of course, go ahead, please.
I admit to being momentarily distracted by the invocation of Miss Frizzle as epitomizing science, but nonetheless, I'd like to understand a little better what was the comparison you were making specifically between those two versions of Pythia 1.4b and 2.8b. What was our takeaway from the comparison between those two?
Oh, so yes, thank you for the question. I don't think I was trying to draw any comparison between those two sets of results. I was just trying to note that even as I scale up the size of the model, we still see this result. So it's not like something that only happens with the 1 billion-ish range of models, but with 2 to 3 billion parameters, you still see the same thing as well. Does that answer the question?
Great, thank you.
Yep. Um, all right. So this was the part of this project where we came up with a bunch of hypotheses and kind of slowly eliminated all of them, except for one. And I think that like I want to sort of I could just tell you which the what we find the most compelling one is. It's H6, as you can guess by the ordering of them. But again, I think I want to sort of get at why this is actually a much more subtle and interesting question than it might seem initially. So um, the first sort of question or the first idea you might have is say, okay, um, is there some sort of intrinsic value of on-policy feedback, right? Like, if you're like a reinforcement learning theorist, there's like a lot of separation between like offline RL and online RL. But and people will sort of use words like coverability or concentrability, and I don't even know how to spell either of those words, but they mean things. I'm sure Wen could tell you what they mean. But the sort of difference between that setting and what we're thinking about here is that I don't actually get real reward labels in this setting, right? The on-policy labels are just imputed by this reward model. There's no like ground truth reward here, right? And this is from a reward model trained on the same data as the policy, right? So it's kind of weird to think that somehow you're somehow getting on-policy feedback in a way that isn't already contained in the policy that was trained on the same data. And furthermore, you like can't create any new information via sampling, right? Like by information here, I mean like ground truth, real human preferences, right? All I'm doing is just like, generating autoregressively. I'm not getting any like real new human preferences in this whole procedure. Um, and this is again sort of connected to back what I was saying earlier about the sort of once we had the reward model, we're almost like information theoretically done, right? Like once I had the reward model, in theory, I could just run a tabular value iteration procedure to compute the policy, right? I can't create new information via this sort of sampling thing. Um, I think my favorite way someone has phrased this actually came from faculty here at Cornell, where that people seem to sometimes view RLHF as a perpetual data generating machine. And when I first saw this tweet, I think I was a bit annoyed by it, but in hindsight, I think it's very wise and sort of probably the most accurate way to respond to the simplest way of trying to view what the answer to this question is. So, okay, so hopefully I've convinced you that that is not the answer here. Okay, let's keep going. So another answer, which various folks have put in the literature, including myself in a past paper, is that offline preference fine-tuning algorithms fail to regularize to the reference policy. The easiest way to see this is if we just look at our objective here, okay, our usual sort of likelihood maximization, but then we kind of bring back this sort of this prior regularization, right? Observe that reverse KL has an on-policy expectation, right? Like I'm actually sampling from my policy and querying the reference policy on that, right? But a purely offline algorithm never gets to see samples from my policy, right? So unless my offline data set somehow magically covers everything my policy could do at test time, it's unreasonable to believe you could actually bound the reverse KL. If you want a more formal version of this, I recommend you check out um, the paper that I'll link in the related work from Yuta on this stuff. I think this is true. I think you can do a bunch of experiments that show that you do a worse job of controlling the KL to the reference policy when you have an offline algorithm. But going back to the results I showed you guys earlier, I'm using the same regularizer for all experiments. So this can't explain the results I just showed you. I'm going to start going to the next few hypotheses a little bit more quickly. Various folks have argued there's something fundamental about online optimization that's easier. We use the same optimizer for everything. That can't be the explanation here either. Another explanation is that reward models can be trained on a wider data set. This is true in practice in the sense that oftentimes you will see people use reward models that are trained on really wide distributions of data compared to what you used for the policy training parts of things. But this begs the question, why couldn't I just use that data to train the policy in the first place? And sort of relate this, you'll still see a gap even when we sort of created the data set ourselves and controlled things. There's sort of more kind of experiments to sort of like try and falsify these hypotheses in the paper. I can talk about any of those if people are curious offline at some point. Maybe the last hypothesis I want to discuss is that reward models somehow generalize better out of distribution than policies, right? Intuitively, if you believe this, you would say, okay, now I'm just getting better feedback kind of on whatever my policy sees somehow in a way that I don't get from just doing policy training directly. The way I'm going to measure this is basically by looking at how when we use the policy learned by DPO as a reward model, how good its best event performance is. So this is, on a distribution of samples it wasn't trained on, so it's some kind of OOD. And what you will see like fairly consistently is that kind of global structure level reward model, just a standard reward model, has much better best event performance than either a DPO reward model or what we call a local reward model in this paper, aka DPO without the prior regularization. You still see this. You see this kind of very distinct gap. I'll note this is also not just a thing you'll see in my experiments. If you look at the top of the reward bench leaderboard, which is like a public leaderboard for ranking word models, you'll see the exact same thing there. So this initially seems, I think, really compelling, and it's an argument I think various folks have made. But I think you'll have to then answer the question of why it actually generalizes better OOD, right? Like we haven't actually answered the fundamental question yet. And I think one ablation that we were sort of surprised to see hadn't been done as much in prior work was that they also generalize better in distribution. In the sense that if I just look at the validation likelihood, you also see the exact same ordering of things. And, a variety of folks have argued that essentially if you have better margins in distribution, you should expect better out of distribution performance. You can really think of it as just like maximizing the margin of your classifier. So you should be robust to kind of perturbations. So I think these observations are true. And the first set can be explained by the fact you generalize better in distribution, just to like a validation set from the same distribution. But I don't think we just kicked the can down the road, right? We haven't explained why you generalize better in distribution. So in the last 10 minutes, I'm going to try and argue what really I think is fundamentally going on here. And I am going to argue that this is really something to do with improper and proper learning, which is a term from kind of statistical learning. Don't worry if you haven't heard of it before, I'm going to go through it more carefully. But also this idea of sort of a generation and verification gap. So if you've taken like a CS theory course, you've probably heard about things like P versus NP, right? P is problems for which we think generation is easy, meaning polynomial time. And NP is problems for which we think verification is easy. And if we kind of like most people believe that P is not equal to NP, there's problems that are sort of in this that are in NP but not in P. So they're problems for which we can verify easily, but we can't generate easily. And a lot of practical problems kind of have this flavor, where it's easier for me to check that I did the right thing than to give you the right thing in the first place. And I think that if you believe that this is true for certain problems, and I'm going to give you evidence it is for summarization in a bit, but if you believe this is true for certain problems, it means that our kind of picture from before is sort of missing a few key parts. So if I bring back what we had before, um, we can really think of policies here as being generators, right? They're actually giving us the full trajectory. Versus we can think of reward models here as really being just verifiers, in the sense that given a trajectory, they tell you how good it is. They do this sort of post hoc inference rather than giving you the good thing in the first place. And if we believe there's a generator verifier gap, we can also believe that there's maybe a simpler set of reward models within our overall space of reward models that can accurately sort of represent the underlying reward function of whatever it is we care about. Now, I think the most natural question you might have here is that like, okay, but how do I actually get a sample complexity benefit if I'm still looking over the same large R class? I'm going to be very hand-wavy here, but a lot of folks, for a variety of reasons, have argued that deep learning can learn simpler functions with fewer samples, in the sense that like sort of the kind of a uniform convergence-based argument couldn't explain. So what this means then is that there is then some subset of policies, I'm going to call it pi of R sim, which is the subset of policies that are soft optimal for this something in this set of relatively simple verifiers. And then really what I think you can think of RL as doing is taking this relatively simple verifier and then projecting it over here under this reverse KL metric to the space of this sort of subset of this full space of policies. So if looking at this picture, you might ask, why can't I just directly do maximum likely estimation on the subset of policies that are optimal for relatively simple verifiers? The challenge is that I have no idea how you do that, right? Like, how do I say, pick a policy that is optimal for a simple reward function, other than by learning a simple reward function and then computing its optimal policy? So really, what I think the benefit of RL in fine-tuning is that from a statistical perspective, it means we only have to look at this relatively small set of policies rather than the whole policy space. I'm going to state this in words now, but this is maybe the intuition you should have in your head. That I'm not going to read out this whole thing, but if you aren't going to as well, here's the TLDR. It's that maybe all these things lead to likelihood, but RL lets us take a shortcut, since that it lets us, from a statistical perspective, only look at a smaller set of policies. Just the ones that are optimal for relatively simple verifiers. So I'm going to give you now maybe some evidence that A, there is a generator verifier gap on the problem I've been looking at. And two, when I remove this gap, we instead see online-offline performance collapse to the same thing, which is what our initial set of information theoretic results predicted. So one thing that's pretty interesting is that you can essentially do a scaling study in terms of the size of the reward model and the size of the generation policy for like best event performance. Turns out that you can use a reward model that is much smaller than the policy. In this case, I'm generating from like a roughly 7 billion parameter policy, and I'm using a reward model that's only just like 1.4 billion parameters. And you'll see no difference in performance versus if I'd instead used the reward model of size like, 7 billion parameters. So this means that, likely speaking, this sort of simpler function, the reward function here is simple enough that it can be accurately represented via this relatively small verifier. The flip side is also true, that I can use a reward model that is much larger than the policy, and I see no improvement in performance. So there appears to be this sort of like fundamental gap in terms of the complexity of these two different things. Okay, so you might say, cool, that's neat. But can we use this hypothesis to predict sort of other new results? And I'm going to argue there's essentially two easy ways for us to sort of like close this generation verification gap and then show that this leads to online-offline algorithms having the same performance. So the first is that we can just simplify the policy. So think about like a one-step bandit problem, right? There, the reward model and the policy must be of equivalent complexity because given one, it's just like a softmax or a log to go to the other one, right? They're like basically the same thing. So what you can do is just think of like scaling down the horizon of the problem you're trying to solve, scaling down the maximum length of the completion you're trying to generate. So what we did in particular is we just tried the task of basically generating 2-word summaries rather than like 20 words or whatever the usual limit is. And while the gap doesn't go to 0, it is far less significant. It's within like 1 point than it used to be. So you can also try the flip, which is you can try making the reward function more complicated. So the way we did this is we used a set of kind of ground truth reference summaries as targets, and we computed like a metric called Rouge that basically tells you how many words in that do you have an overlap with. This means sort of the minimum complexity verifier needs to actually include all those reference summaries somewhere in it. And if I had that sort of lookup table from prompts to reference summaries, policy would be trivial. I could just kind of read off from that table. And in this setting as well, you again, gap actually go to 0. So TLDR of that is that when you have no generation verification gap, you see sort of like equivalent performances here. So I think that is all I wanted to say here. Purposefully, I've sort of made everything here like relatively informal in terms of the way I've been talking about things. The paper for this should be out on arXiv maybe like Sunday, I guess. If you want to speak, here is a QR code to a copy of it on my website. Thank you guys for listening. I hope it's clear why this problem is not as easy as initially might seem, and there's a lot of sort of nuances and details you have to get right to really get to what I think is the heart of the matter.